not this. We'll come to the next one. This is really to get a little bit of background in what's error correction so that you don't get too shocked when we move on. So I don't think anybody does this particular kind. The next one is the internet checksum. And we saw this a couple chapters ago. So all you do is that you have a bunch of data and you just calculate 2's complement sum. Okay, you just basically keep adding, but you don't carry, and then these become your error correction bits, and then you check on the other side again if the error correction bits match and if there's an error or not. Okay, so this is really used at transport layer, not at the link layer that we are talking about, but that is another error correction, or not correction, error detection plan. Okay. So it's there in UDP as well as TCP, so not going to discuss this more. What's new with link layer is something called cyclic redundancy check. It's a more sophisticated scheme for error detection and correction. And we will come back to this question in a couple of minutes. Why do we have CRC in link layer and internet checksum at transport layer? But let's first understand what the CRC is. So there's a lot of maths involved here, but we will skip most of it. Think of data as D bits as a binary number. Fair enough. So this is your data, and these are the so-called CRC bits. Choose a pattern generator. So there's a magic here. G is another binary number that you pick for a particular scheme. Okay, so let's not worry about where the G comes from. Some mathematician tells you this is a good G, you can use it. Okay, so your goal is that now you have D, which is the data, G, that is a constant. You want to come up with the CRC bits such that dr is exactly divisible by G. Okay, so you want to come up with these so that when you try to divide this by G, which is this here, then there is no remainder. It perfectly divides, except that the division is modulo 2, and we'll illustrate. Modulo 2 division means that when you do a subtraction, there's no carry. Okay. So that makes the task of the receiving side very easy. All the data is coming in at full speed. All you do is you have this fixed number. You don't even worry about these distinctions. You don't recalculate CRC or anything. One big number comes and you divide it by G, and if it divides, great. If not, it's corrupted. Okay. So the only thing left for us now is how do I find these? You're given G, you're given the data. How do I find the CRC bits that this property is true? Okay. So first of all, let's try to find a mathematical way of expressing this. Okay. So what is D 2 to the power R? Here R is the number of bits in the CRC. So multiplying something by 2 to the power R is same as doing what to that number? Shifting R bits, right? So multiplying by 2 to the power R is shifting R bits. So what this is that all this followed by zeros, R zeros. Shifting R bits, same as putting R zeros in the end, right? And then so if you XOR it with R, you basically get D bits followed by R, whatever it happens to be. Okay. So all I'm saying is a mathematical way of expressing this number where D bits have been appended with R, small r bits of the CRC is essentially D 2 to the power R XOR R, because if you basically if you have R, you XOR with zeros, you get R. You XOR something with zeros, you get the same thing. So okay, that's one way to put it. D followed by R is essentially D to the power R XOR R. So the number that we came up with was D to the power R, D to the power XOR R, okay? And what we said was that this number should be divisible by G. This is same as saying it's N times G, right? Something is divisible by G is some integer, some constant multiplied by G has to be that number. So this is basically the not complete details of the mathematics, but to give you an idea. So let's try to develop this further. And XOR R both sides. Okay. And so you XOR R, you XOR something with the same quantity twice, you get the original number. So this becomes D2 to the power R, and this becomes NG XOR R. Okay. So let's think about this for a second. What this is saying is D2 to the power R is multiply some number of times G, then XOR R. So it's equivalent saying that, and XOR R is like appending those R bits in the end. So if we divide D2 to the power R by G, then we'll get N as the quotient and R as the remainder. Okay. So if you can't follow everything, just basically remember this. And quotient we don't care about. All we care about is R. R is our CRC bits. Okay. So if nothing else, just remember this, that if you are given a number D and the G, then you want to find the R. This is the CRC. You divide D2 to the power R, basically D shifted R bits by G, and the remainder is your CRC. Okay. So here is an example. You divide. This is D. This is G, and so 2 to the power R means you added 3 zeros, and you keep doing the long division. The one thing is that let's see. So the division is there's no carry in the division. Okay, so I'm trying to look for an example. 1 minus 1 is 0, and so every step of division is just an exclusive OR. Okay, so 1 0 is 1, 0 0 is 0, 1 0 is 1, and so I think it's instructive to look here. 1 1 is just 0. Okay, so that's why it doesn't count. It's not, the carry is ignored. You don't have a carry 1 or anything. You basically, every time you're doing subtraction, it's just basically an exclusive OR. Okay. So that division look okay? Find any problems anywhere? So so finally, remember, this is your D. What you're going to send is 1 0 1 1 1 1 1 0 1 1 1 0. That's your D, and then you'll append it by R, your CRC bit 0 1 1. Okay, and when you reach the other side, The other side does something very simple. It already knows G. So it takes that G and divides this. The G is again 1, 0, 0, 1, and sees if there is a remainder or not. So try to check this. The way you check it is that the final thing you get should be completely divisible by 1, 0, 0, 1. The